Hi everybody, welcome to week 3 of our webinar. This week we're going to broach the topic of step 2, making checks of data integrity. As always, William O'Bannon of StatsWhisperer here to bring you some statistical knowledge. There we go. All right, so as always, we want to keep in mind where we are in this 6-step process of data analysis. So as we said last week we addressed data entry and cleaning, right, step 1. And then step 2 is the check of data integrity, which is this week. And for our parallel process, we did data entry and cleaning for dating analysis last week, and that reflexively is the check of data integrity. So just to kind of make an illustration for the checks of data integrity, if this was dating analysis or data analysis, right, we would want to make sure that there's no threats to integrity for the person we're sending out on dates, such as a Pinocchio nose, which is an indicator, right, an indicator of a threat to integrity, at least through the Pinocchio story it was. So we want to make sure there's not a threat to integrity, but actual integrity for dating, right? So that's the parallel to the process, and that's the level of importance, right? It's very important. You want to be responsible with people's welfare, and it's the same thing with data, because our practice decisions and important decisions like that are based on data too. So people's welfare will also be impacted based on our assessment of data integrity, right? So is the data appropriate for analysis? Because if it's not, and you use it for analysis, you could end up with false findings, which could lead to bad practice decisions, right? So we want to make sure there's no threats to our data integrity. And in case anyone's wondering, that's a man with a steamroller about to roll over our data integrity. So he's a threat to our data integrity. Now, of course, that's just a little symbol for us. The real threats to data integrity, right, are listed here. Now, the first one is meeting test assumptions, and that's what we're going to talk about tonight. And you'll see that's a very big topic with a lot of subtopics under it. And it takes a great deal of thought and preparation. It's probably one of the most thoughtful and time-consuming parts of a research study, especially if you're using linear regression. But most of the time, if you read a journal article, it's often not reported, and I suspect it's often actually not done, because there's nobody teaching, these steps. Like first you do this, then you do that. So what a lot of people do is they'll get the data and they'll just start doing linear regression right away. And that's a real threat to the findings, because the findings could be way off just by a few small threats to the data integrity. But that's not going to happen to us, because we're going to go through each step. Now, the other part we need to discuss to review data integrity, we need to also assess missing data. This will be not tonight, but later on. Assess missing data, right? So if there's missing data, especially if it's missing in a pattern, like say like male or female are less likely to provide data, and there's an underrepresentation of gender or some other variable, that's a real threat to data integrity, right? Because we want to generalize to the whole population our findings, but if data is not provided, say, by males, then we're generalizing to the whole population when our findings have to do more with the female portion of the population. There's the power analysis. that's to tell us how many people we need to pick up on a relationship between two variables. So if we were looking at gender and happiness, right, and we had 2 males and 3 females, and we asked them how happy they were, and then that was our study. Depending on how happy the 3 and 2 were, you would say, well, that's not enough people to measure, how happy men and women are. Well, how many people is enough people? That's what power analysis tells us. And it's actually much more simple than people think, at least the early stages. And then lastly, the fourth dimension that we want to consider when we look at data integrity are our measures. Now, this is gigantic, of course, because if the measures aren't measuring the construct, then the whole study is nil, right? So if we want to study happiness, but our measure of happiness doesn't reflect happiness, what are we studying? Right? We're just studying nothing, really. But the thing is when you show people findings, what's the first thing they start doing? They start trying to make sense of the findings, right? So if I say eating fruit makes you happier, then normally people start saying, oh, well, that's because, bananas have potassium and, and things like that. The first thought usually isn't, well, how is happiness measured, right? Oh, happiness was measured, by how often you smile in a day, right? So that wouldn't be too accurate, right? Somebody might be grimacing in pain. You never know. So yeah. So these are really big categories of threats to data integrity. So, and tonight we're going to go through the meeting of test assumptions. So the meaning of test assumptions. So we have that first category, right? We have a category 1. Then as soon as we get it away from the other 4 categories, guess what happens? It breaks into a bunch of subcategories. And each subcategory has many details and considerations. So that's why we're going over meeting test assumptions. So we're going to look at so every test has different assumptions, right? Or different combinations of assumptions, right? So we're going to look at linear regression, the assumptions for linear regression, because we're using logistic regression and linear regression in our analysis in this program, and the assumptions for logistic regression are much more relaxed than linear regression. So we want to look at linear regression because if we understand everything about linear regression, we could do the other tests. So some of the big assumptions of linear regression, the big ones you must check, is a normal distribution, which means if you have a continuous variable, it has that bell-shaped distribution of scores. Multicollinearity, which means that the independent variables are not too highly correlated with each other. And I'm just mentioning it now so it'll sound familiar when we officially cover it. So right now it's just a little context. I'm just mentioning it. So some people might say it doesn't make any sense, but subconsciously it's starting to sink in. So when we get to it later, it'll be better, right? Then homoscedasticity, excuse me, that's a rather long word, and linearity. So if we're going to do linear regression, we need to do each of these checks before we can even do the regression. Now, remember I said that the category breaks into subcategories, and then the subcategories break into more categories. Pardon me. So a normal distribution, right? So a normal distribution is part of the test of assumptions, right, which is part of checks of data integrity, right? So we're going down a path here. So a normal distribution. The first thing we need to discuss is how do we test for normality? So normality means that the distribution is normal. It's kind of used interchangeably. The next thing we need to do is say, hey, how do we identify outliers, right? Like scores that are really big or small compared to everyone else. That's often what threatens the normal distribution. And lastly, if we have a variable that's very non-normal, number 3, we might want to transform that data, do a data transformation. So when people look at normal distribution, right, these are what they're thinking, or what would be good to think is we're going to test for normality, see if the distribution is normal, see if there's any outliers, and then consider making data transformations if appropriate. So the first one, testing for normality. How do you do that? So the first thing is let's see what a normal distribution is. So this is what it is. So when we test, we want to see if the distribution looks like this, and if it doesn't, is it significantly unlike this, or is it kind of like this, right? Or is it like this, right? So if it's kind of or like this, that's good. So what this is the breakdown. So this is what is commonly referred to as the bell curve, right? The term being behind the bell curve, right? That means you're to the left of this distribution, right? The low side. That's where that comes from. So the normal distribution, right? So what we see here on the bottom are standard deviations, which are measures of dispersion from the mean. So 0 is the mean or the average score, right? So if 0 is the average score on a depression test, right, you would see how many people were to the left and the right, right? So the very top, right, so we have the -1 and +1, right? So the right outside the zeros, and if you look at the top, there's a 68%. So what that's saying is, in a normal distribution, 68%, or about 2/3 of the distribution, is about 1 standard deviation from the mean, meaning 2/3 of the people are kind of centered around the mean. And then you'll see under -2 and +2, right, there's 95%, which means in a normal distribution, 95% of the people, like on a score of anything, like if it was an IQ test, depression test, anything, would be 2 standard deviations from the mean. And then the 3 standard deviations from the mean, that's 99.7% of people. So often you'll see later, we define outliers as those outside 3 standard deviations from the mean, because they're, 0.03% of scorers. So we would call, and then if you took the whole population, there would be 4 standard deviations, where I believe it's something like 0.0001% of scorers are 4 standard deviations from the mean, right? So this is what we would like our continuous variable to look like, the distribution for our continuous variable. So if we looked at happiness, right, these would be the distributions. Now the threat to a normal distribution, poor skewness and kurtosis. Poor is in not good, that you have sympathy for them, right? Like not good, skewness and kurtosis, right? That's what threatens our normal distribution, and I'll define those. So the skew, excuse me. So the skew, rather than giving it a definition, let's just look at what it is. As we saw in that normal distribution, there's a peak in the center, right? Because that's where most of the average score is, right in the center. So in a normal distribution, the tippy top is right in the center. A skew is when the center either favors the right or the left, right? So we could see the first distribution is negatively skewed, right? And then the second distribution is a positive skew, right? But either way, it just means that the point, the top, is not in the center. It's either favoring the right or the left. And that skewness is a threat to the normal distribution, right? The normality of that curve. Now the second threat is kurtosis. Now, kurtosis it does not refer to the peak favoring one side or the other. So the skew is the peak, but the kurtosis is kind of the distribution. So we see C in this letter C for the kurtosis. The peak's too high, and when the peak's too high, that means there's too many people at the peak, and that you can see the lines right there, right? The lines move down here. That means the people here are missing. So where it would be normal, they're missing, and they're up here. So that means it's too flat, right? Like the dispersion is too flat. That's the kurtosis, is how it's dispersed. It's too flat. Now B, that's good kurtosis, right? So you can see there's the peak, our peak, right? And then it goes down just like the normal distribution, right? So that's good. So if it was A here, right, that would be good. If it was C, it would be too high. And then if it was B, that's too low. You'll see it's kind of shaped like a semicircle. Right? So when it's shaped like a semicircle, that means there's not enough of a peak, and the people from the peak are over here in the tails. And for C, the people that should be in the tails are way up here. So what we get is A, kurtosis where it's evenly spread out. So peak in the middle and an evenly spread out kurtosis, right? And a threat to the skewness or kurtosis will result in a non-normal distribution. And our job is to figure out, is it non-normal? And if the distribution is non-normal, well, just how non-normal is it? Is it acceptably non-normal, or is it too non-normal? We could test that statistically, right? So we don't have to, you probably wish you had like means to test some of your friends, right? So to see how normal or non-normal a person is, right? You just have to wonder sometimes for decades. But with the distribution, you actually can test right now to see how normal or non-normal a distribution is, right? So there's two ways we're going to do this, right? The first way, pardon me, is with the actual statistical testing. The test is the Kolmogorov Smirnov test. It's hard to do, it's hard to say, and the Shapiro-Wilk test. Right? So these are good and they're widely used, but they're best with large samples. And this actually plagued me for years, but I didn't realize this fact because the tests are what they call very conservative, as in they're willing to call a distribution non-normal very fast, and it's because they're best for large samples. Like the larger the sample, the more normal the distribution, and reflexively, the smaller the sample, the less normal the distribution. So since they're best with large samples, if you have a medium-sized sample, and large as in like thousands and thousands of people large, right? So if you have a sample of 200 or 100 or 50, and you use these tests, they're very likely to say the sample is non-normal, when actually the sample might be acceptably normal by another valid criteria, which we'll look at after this. So in SPSS, and we'll actually do this, in SPSS, you can do this test, okay? So you go to Analyze Descriptive Explorer, you enter the variable, and under Plots, you check Normal Plots with Tests, continue okay. So let's actually do that. So we have our study here. This is my famous dogs and cats study. So we go to Analyze, right? Pardon me, sorry. Right, Descriptive Statistics and Explore. So here we go. We're in Explore. So if we stretch this out a little bit, or not, then we find age with the outliers in it, right? So this is age. So this is the age of the study participant, a nice, easy to understand variable since all of us have an age. We put it in the dependent list. Remember that I said under plots, we click that. We don't need the stem and leaf right now. We click, right? So this is what we click. The normality plots with tests, and the tests are the two we mentioned. So continue, and then OK. So there we go. We have our Explore, and we scroll down a little bit, and there we go. So right here where it says tests of normality, right, here's our results. And I actually have it in the slide, so this will be right in the slide. So here we go. So we did that. And then this is what we just saw in the output. So the output tells us for the first test, right, the significance is 0.000, which is below the standard 0.05 level of significance. And for the second test, it's 0.00, which is below the 0.05 level of significance. So both tests are saying the test is significant. The trouble is what are we testing for? A non-normal distribution. So it's saying that there's significant evidence of a non-normal distribution. Now each of them tests the skewness and kurtosis. So what it's saying is the skewness and kurtosis are significantly off. Right? So that's a challenge. Now the other way to test for a normal distribution, and this is the way I like to go, is to look at the actual skewness or kurtosis, right? The actual. So instead of testing them, to actually look at them, look at the values for skewness and kurtosis, and see if each of them is 2 times larger than their standard error. And this is kind of a loose rule. Sometimes they use 3 times larger than their standard error. But the trick is if they're not 2 times larger than the standard error, then it's approximately normal. And this is good because this technique can apply to all samples. So not just big samples like the other tests, but moderate and I guess even small samples would be okay. So how do we get the skewness and kurtosis values, right? So we just go back to SPSS and get it. So analyze descriptive statistics, frequencies, right? Then we put in age. Then under statistics, just check skewness, kurtosis, continue, and OK. So we go back, analyze descriptive statistics, frequencies, then age, put that over to the right, and then under statistics, we check skewness and kurtosis, and continue, and then just check OK. And there we have our values, right? So skewness, 0.568, then the standard error, the skewness is 0.241, then the kurtosis is 3.386, and the standard error is 0.478, right? So let's go to the slides. So I put those on. I just thought of everything. So I put those on there, right? So there we go. So there's our values for the skewness and the standard error, the skewness. Right? So we take them and we divide the skewness by the standard error of the skewness, which means we divide 0.568 by 0.241, which equals 2.36. So it's right around 2. Remember I said sometimes people even use 3? So if it's right around 2, that's approximately normal, and that's for the skew. So what it's saying is that the peak right, is approximately normally in the middle, right? Exciting. So then the next one, the kurtosis, right? So it's 3.386 is the value of kurtosis, and the standard error is 0.478. Now when you divide that, it's 7.08, which is much higher than 2, much higher than 3, right? So it's significantly non-normal, the distribution in terms of the kurtosis. So it's not appropriate for regression analysis because the distribution is significantly non-normal, right? And specifically where? In terms of the kurtosis, right? That distribution that the dispersion where it sort of looks like a half circle, right? That's our challenge. So then we might want to say, hey, let's look at the actual distribution, right, instead of speculating about it. So we go to the histogram with the normal curve, which is right in the descriptive statistics, analyze descriptive statistics, frequency, and age, right? And then under charts, we click histogram and show the normal curve on the histogram and continue in OK. So we go back here, just go to Analyze, Descriptive Statistics, Frequencies. Then we have age in there, right? This is the same place as before. Then under Charts, we go to Histogram and click Show Normal Curve. Then we click Continue and OK. And then we get the actual distribution of scores, right? So that is also in the slides. So I'm going to take this back to the slides. So there we go. So if you look at our histogram of the distribution of age, we can see the peak. Yes, it looks like stuff is pretty much in the middle, right? That's good. That's our skewness. So that matches with that story. But then we have a, hey, what's going on here? On the right and left, you can see there's two, right? There's one way back here near the 35. And there's one over here past the 50. Those are the outlying cases. You see there's the normal curve, which says if this was a normal distribution, everybody would fill out this curve, right? So these don't really fill it out, but they're kind of where they should be. But these scores, they're way out in left field and right field, right? They're way out away from the curve, right? And that makes sense because our kurtosis is our challenge. What's the kurtosis? It has to do with the dispersion. So these are too far dispersed, right? So notice outliers, right, outside the curve, they're impacting our kurtosis. That's why our kurtosis is funky. So how do we make the distribution normal, right? So if it's non-normal, perhaps the first thing we should try is to remove the outliers. And then after we take a step to make it normal, of course, we have to retest the variable to see if it worked. Right? So to remove an outlier, first you must identify the outliers, right? Who are these people, right? Who are these outliers that are way out there, right? We have to figure out who they are. And there's two ways we could do it. We could do it by hand, by computing the mean and seeing who's 3 standard deviations above or below the mean. That's because we said, remember, 99.7% of cases are in 3 standard deviations. So the ones outside that 3 standard deviations are outliers, right? And that makes sense because we see they're at the ends of the distribution. And then the other way, and a lot of people like this a lot, is the old box plot, right? The box plot is when you do the little chart, and the little chart tells you, they point the little points out, right? So we'll do it both ways. So you'll know both ways. Interestingly, you'll find that the stem and leaf plot, right, And the other method of 3 standard deviations usually identify the same cases as outliers. The only difference is the stem and leaf plot is a computer saying these are the outliers, and the 3 standard deviations, you're figuring it out, by hand. Not that it's a long computation, but you're just naming them yourself. So first, let's look at identifying outliers via computing the 3 standard deviations above and below the mean. So to do this, first we need the actual mean and the standard deviation of the variable which we're studying in terms of its normality. So this is the third time we've gone to frequencies, right? So analyze descriptive statistics frequencies, and we have age in there already. Then under statistics, we click mean, the standard deviation, and then continue and OK. So let's go to that really fast. So analyze descriptive statistics frequencies, and then statistics, standard deviation checked, means checked, yes. Continue, and then OK. So there we go. So the mean is 100 people. The mean is 43.25. The standard deviation is 1.935. So if you round that up to 1.94, that outlier is going to be 3 standard deviations, so 3 times 1.94, whatever that number is, added to the mean, so that's above, and subtract it from the mean below. So let's go back to our slides. Okay, so we have that. So here's the mean we just saw. So this is what the frequency distribution looks like. So we have the age, the mean's 43.25, the standard deviation is 1.94. Now whenever you do that statistic, you get the frequency table below that tells you how many people are in the actual ages. This is only part of it, but so 37 years old, 1 person. 41 years old, 21 people. 42 years old, 15 people. Right, so, but what we're interested in is, right, so we multiply the standard deviation by the numbers of standard deviations we're using to define the outlier. So usually it's 3, right, because we saw most of the people are inside that 3 standard deviations. But for a small sample, you might want to make it 2 standard deviations. And for a very large sample, like I said before, you might want to make it 4 standard deviations, right? But 3 is our number tonight. And we're going to add and subtract our computed number from the mean. So our step here, third, we're going to multiply the standard deviation by the number of standard deviations. So we have 3 standard deviations, so it's 3 times 1.94, which is our standard deviation, which is 5.82. So 5.82 above, right, so 43.25, which is our mean, plus the 3 standard deviations, which is 5.82, is 49.07. So in terms of age, anyone over 49.07 is 3 standard deviations from the mean age and an outlier. And then under, right, it's 43.25, which is the mean, minus 5.82, which comes out to 37.43. So anyone under 37.43 is an outlier in terms of, younger age, right? So then, remember I said they had the frequency distribution where they told you how many people, like the 1 person was 37, and 21 to 41. Well, that's what we have right here. And we could see here's our cutoff of 37.43 right here. Here's our cutoff. So how many people are outside of that cutoff? Just the 1 person. Here's someone's 41, and anyone younger than that, just 1 person. And they're under 37.43. They're 37. And then we go to the other side, and our high mean was greater than 49.07. So here's that break right here, 46, and then there's no one that's 49, but there's one person over 49. They're 52 years old. So we have one outlier high and one outlier low. So we want to remove them and then retest for the normal distribution. But before we do that, we want to also just identify the outliers via the stem and leaf plot, because they're going to tell us, you know, that the same people are outliers, so we don't need to test that twice. So the stem and leaf plot in SPSS, right? So we go back into our Explore, Analyze Descriptive Statistics in Explore. We put in age, and then under Plots, we're going to click Stem and Leaf, and then Continue and OK. So here we go back there. Descriptive Statistics in Explore. And, right, so here's Plots. This we clicked before, but, right, remember we clicked it for the normal plots. Now we're going to click it for Stem and Leaf. Continue and OK. So if we scroll down a wee bit, there we go. There's a lot of findings. So here's our plot that tells us our outliers. So there's one, and there's the other. Let's go to our slides. That's right. There's the one, and then there's the second one. Now, just what does this mean, right? So there we go. So what it's saying is the little line in the little box, that's the median value. This is the top 25%, the little T on the top. The T on the bottom is bottom 25% of scores, right, younger ages. And then the 50% in the middle. And then we have our outliers. There's the outlier for high age. There's the outlier for low age. And they're the exact same too. They're the 37 and the 52-year-old. And you can see it right here, because on the side, there's 35 and 40, right in the middle, 37. And there's 50 and 55, right in the middle, 52. So now what we want to do is we want to remove those outliers and then retest for normality. So in linear regression, I like to do the analysis with and without the outlier. So I like to leave them in if at all possible. So if I remove them and it's a normal distribution, I'll do the regression with the variable without the outliers and with the outliers. And if there's no difference in terms of findings, like if it's not remember the last dot here, there's more concern if the findings are different. That means if it's statistically significant with or without the outliers, then you should probably leave them out, right? Because the outliers are affecting the findings. But if it's significant with them and without them, or not significant with them or without them, then I like to leave them in. So I like to leave them in if I can, but that's only appropriate to me if they're not changing the findings in terms of the findings being significant or not. We'll probably see that in analysis later. So we retest after the outliers are removed, right? And for the Kolmogorov, Smirnov, and Shapiro-Wilk, they're still significantly non-normal, right? But like I said, that's made more for big samples. And like I said, not a lot of people realize that, and it drives them bonkers because everything's non-normal, and they feel like they need to address that. But if they knew this method, right, like you know now, the skewness and standard error, they might be okay, right? So we look at it now. Now we take the new skewness, which is 0.568, and divide it by the new standard error, the skewness, which comes actually to 0.07, right? So it's really far below 2. It's right. So when it's 0, that means the skew is right in the middle, right? It's not negative or positive. It's right in the center. So that's great. Now the kurtosis was our big challenge. So let's look at the kurtosis. So we now have a kurtosis, which is, let me see, hold on a second. So you now have a kurtosis, which is negative 1.39. Negative and positive doesn't matter here. That just means in the direction skewed, divided by 0.483, which is 2.88. Remember when I said sometimes they'll make it even 3 times as larger? So it's right between 2 and 3. So there was 100 people in the sample. Just by removing those 2 outliers, the variable is now approximately normal and appropriate for analysis. Good job. Now the data transformations, right? So if we have a non-normal distribution, many times people want to do what's called a data transformation. And this is something that you have to be very, very careful with. The data transformation mathematically transforms the variable. It'll multiply all the terms, all the values, right? Like the values for age by a certain number to make them more spread out and even. The trouble is, though, is you see where it says complicate interpretation? The trouble is, though, is when it multiplies those numbers and they spread out, those numbers are no longer interpretable. Right? So if the average age is 42, if you do a data transformation, the average age might become like -6 or, or it's like 500 or something like that, where it's not interpretable. And even if it's just off a little, like if the average age is 42 and then it's 60, obviously it's not as meaningful. You're not getting the actual values in the population. So I really like getting the actual values in the population. So I'm kind of, I don't do too many data transformations, but you should know about them. And like I said, you could also do the deal where you do the data transformation and then test, the variable to see if there's any significant differences in using the transformed and untransformed variable. I'll say that a few times because it's a very important point that not a lot of people know about, right? The most common data transformation is the log odds, and that's what we're going to do right now. So to do a data transformation, right? This sounds like it is sophisticated stuff. So to do a data transformation, you go in SPSS to transform and compute variable. Under the function group, select arithmetic, and we'll do this. It's much more meaningful. Then under function and special variables, right, LG10, you move that up, and then you put the name of the variable and rename it and click OK. So let's actually do that. Okay. So we go to data. Nope, transform, compute variable. Oops, I already did it. Get rid of that. All right. So we go here and we select arithmetic. When you select in the function group arithmetic, these appear. And LG10, that's our log odds. So you click on that, and then you move it up with this arrow. Then it's up there, and you have to rename it. So we're looking at the log odds of age. So you might just call it log age. And then you have to put age where the question mark goes. So age with the outliers. Then you click there. So it says I'm going to take the logarithmic of age, right, with the outlier. That's what we're trying to compensate for, is the outlier. Then click OK. And then you will see in our variables, right, here it is, log age. And also in data view, you could see right at the end, log age. Now you see, let me see, let me scroll over to age. So you see 37, 41, right? They're all pretty, and then now the scores are 1.57, 1.61, right? So it changes the values very much so. So they're not interpretable the same way, and that's really kind of the big drawback. So then we want to save it, right? We save it, and then, right, so we got that. So there are right, so it's not as meaningful. I know I keep saying that, but it's not. And so it changes our means, our standard deviations, and everything. So after the log odds, we want to transformation. We want to retest the transformed variable for normality. So we do it the same way. So you could even see that the tests here both indicate still significantly non-normal, even with the log odds transformation. Also, even if we apply our other criteria, while our skewness is still okay, the kurtosis is still 5 times its standard error. So the kurtosis is still significantly non-normal. So the log odds went ahead, and not that it does this every time, but it went ahead and not only changed our values so they're not interpretable, but it didn't even really fix, for lack of a better word, the challenge we had with our kurtosis. So like I said, if it did fix the problem with the kurtosis, I would do a regression both ways, with the transformed and the untransformed, same with the outliers, and if the findings were the same, I would like to leave the original variable in there. And I would report, in the methods, right? So we'll get to that. All right, so if the findings don't change, consider leaving the untransformed version in there and report in the methods, right? So you would say the analysis indicated there was a non-normal distribution, right? So the analysis was repeated with a transformed version and the findings did not differ in terms of significance. So you might say, so we decided to leave the original version in, right? And you just report that in a sentence or two and everything should be okay. Right? And then we have our other issues, which are multicollinearity. This is very easily tested for, right? Multicollinearity refers to when the independent variables are highly correlated with one another, right? Which kind of indicates that they're explaining the same changes or the same variance in the dependent variable. So if we were looking at grades per se, like high and low grades, and we have two measures of happiness, we might say that each measure of happiness is explaining the same degree of change in grades. So one of them is unneeded, right? So that's an example of multicollinearity. Right? You have two predictors kind of explaining the same changes or variance in the dependent variable. And that's easy to test for, right? Because in SPSS, there's a function that gives you the tolerance and variance inflation, VIF, right? That will indicate if there's multicollinearity. So the tolerance can't be below 0.10, and the VIF can't be above 10. Right? So simple indicators. So let's go to that. So that's easy. It's just so you go to regression, right? This is all in the slides too, but let's just go through it first, right? So linear, right? So say happiness is what we're predicting. And you have gender, income, and age. And then we go to statistics and just click collinearity diagnostics. This is all in the slides. We'll get to it, but continue and OK. And then right at the end, right, there's the collinearity statistics, right? So you can see the VIF is definitely nowhere near 10, so that's good. But the tolerance is a little below 1. So you're really concerned, with the tolerance is a little low. Not too bad, but but it makes sense because you're looking at income and age, right? And that might be correlated because as you get older, a lot of the times you make more income. So they might be highly correlated and therefore a threat to multicollinearity. Right, so to reiterate, right, so to go to, oh, there we go, the VIF, right, there we go. So those are our values that we just saw. Very good. The next test is linearity, and that's easy. Linearity means the independent variable and dependent variable have a linear relationship, and for linear regression, that's a requirement, right? So remember, linear relationship, so positive relationship is like on the left, as 1 and 2 and 3 and 4 and 5 go up, it goes up on the other side too. And then the negative relationship, right, as 1, 2, 3, 4, 5 go up here, it goes down here. And then the curvilinear is when it starts going up and then it starts going down. Now that curve, that's the big threat to our linearity on this screen, right? Because we want a linear relationship and it's curvilinear, right? So that's what we don't want if we're going to use linear regression. The other term, homoscedasticity, is the homogeneity of the variance, or just referring to the data points are spread out evenly, right? And these are actually easy to test for. To check for both of them at the same time, we would just do a chart showing the residuals in SPSS, right? So we go to Analyze Regression Linear, and then we just enter this in our linear regression model, right? So if we leave our independent variables and dependent variables as is, then we just put in the plots the z resid and z predict pred and the x and y continue, and then that'll tell us, right? That will tell us exactly what we want to know. So regression, linear. Then we go in our plots, right? And these are right here, see, resid, and then so see, it goes out there, and that goes in there, and it doesn't matter which box they're in, the zpred, and we put that in there. Now the interesting thing, you click continue and you click OK, and then you get the printouts here. See the chart scatter plots, right? So this scatter plot where they're kind of randomly around 0, here's 0, they're randomly dispersed, that indicates an acceptable level of linearity and homoscedasticity. Let's look on the slides though. So we did that. See, that's what it sort of looks like. So there's good homoscedasticity and linearity because the dots are kind of randomly located around 0. Now where it wouldn't work out for us is if it looked like this kind of funnel, right? That would indicate that that the dots are not evenly dispersed. They're favoring the right. That would be a violation of homoscedasticity. And then nonlinear, where we have the curve, that would be a violation of linearity. But we don't have that, right? So there we go. So we've checked for all 4 things. So the meeting of test assumptions is done. So I know this is kind of a big one, but it's all written down in the written materials too. And then the 2, 3, and 4 are probably as long as this one was, right? So don't worry, this was a big fish to fry, but we did okay. Okay, everybody, I'll talk to you next time. Okay, goodbye.